All right, I'm gonna go ahead and get started a couple minutes early because Bertrand's got a lot of content to share, so really excited about this. The story I'll tell about Bertrand by way of introduction. So Bertrand comes with a lot of years of very serious software engineering, right? He's definitely the engineer mentality. What I've learned from Bertrand is how to be much more rigorous in how I approach relevancy and much more methodical and procedural about it, and sort of the rewards that gives you of understanding why you're making the changes that you're making to your system. Bertrand worked on a project a couple of years ago where his Solr config file, if you printed it out, was about 15 pages long. So it was an incredible amount of thinking and thought and analysis and tuning and understanding the user intent, all expressed as XML in a Solr config file. So looking forward to what we're going to learn today from Bertrand. So take it away, Bertrand.
Eric, thank you so much for the introduction, and thank you for your mentorship and your friendship. Eric is passionate about not only search and open source, but he's passionate about his company and he's passionate about us, the OSC people. So thank you again. All right, so this is a talk about query parsers, and particularly custom query parsers. So I haven't coordinated with Tom, but kind of Tom on your last slide. If you were here in the previous talk, you talk about the query parser pipeline. So it's actually kind of a nice, maybe, transition. I was very fortunate. I've been very fortunate over the past 6 months or so working with a client who is well represented in the room, working on custom query parser. And so I'd like to share with you, kind of give back to the community what we've learned, the different design options, the pros and cons. And thank you to the client for letting OSC work with you on this. So agenda, we're going to kind of restate the purpose of query parsers in case you don't know what that is. We'll talk about something that is kind of interesting, which is query parser composition in Solr. And then we'll talk about when you need a custom query parser, how to build one. We'll do a little bit of code walkthrough. And kind of finish up with the pros and cons of different design approaches and some closing remarks. So just to kind of sense the level of familiarity with query parsers, I imagine everybody is familiar with query parsers and what they do. Has anybody not seen before a query parser? Of course not. How many developers in the room? You all comfortable looking at code for the most part? Okay. All right. So this is a slide that's borrowed from our training material. We gave this class, actually. I gave this class Monday and Tuesday during the Haystack week here. So just to kind of place where the query parser lives in the ecosystem, right? So on the left side is the index components. On the right side is everything's happening about, during query processing. So the query parser is over here. It's kind of deep into the layers. And it's about matching and scoring, right? We'll see how the query parser relates to text normalization or analysis, and how it relates to the sort of the outer layers of the ecosystem here in terms of the declaration or analytics. All right, so what is the problem we're trying to address here with query parsers? And as we saw in a previous slide, it's about matching. And it's about scoring, right? So these are pretty fundamental responsibilities. But stepping back a little bit, query parsers are interesting because they kind of go at the core, one of the core challenges of search engines, which is to try to understand or try to turn whatever the end user typed or spoke into some kind of code, some code we can execute and perform the search. So the first part of that problem is kind of your classic compilation exercise in any good computer science type of exercise where you have to convert some expression, which could be natural, everyday English or another language, or some more formal language with some kind of grammar, which is not your English grammar, and turn that into an executable. This part is fairly well understood. Again, this is, has been taught in computer science forever. There are great tools out there. They're called compilers. Compilers that generate compilers. Tools like JavaCC, which actually Solr uses for the classic query parser and other query parsers, or Antler. Antler 4 apparently has gained a lot of popularity, so something that a lot of folks use. The second part of the problem actually is more challenging, which is query understanding, right? Again, you're turning into something the end user typed or spoke into something that you're going to execute, right? So you have to have a pretty good transformation process, which is meant at understanding the query. Now, we haven't invented yet a compiler that can go from what the end user thought and what the query looks like, right? So we're trying to basically approach this in many ways. But one thing we can do, though, if you're facing yourself with basically a search application, is to ask yourself how the end users search. Do they search with natural language like we do every day with Google? These days people search by typing sentences, full sentences, as if they're talking to a human. And of course, Google has gotten so good at this. Or are users searching with some kind of sort of more elaborate, formal search language with Boolean operators and or not, proximity perhaps, or even more advanced? I mean, people have invented over the history of information retrieval all kinds of operators to describe an intent. And a lot of times it's actually a hybrid of the two. So some search applications have to actually auto-detect in some ways what sort of language the end user is using. And so maybe you're facing this end user spectrum of sort of skills and usage, where maybe on the left you have your casual, occasional, natural language using users, which maybe are millennials here, young folks used to Google. And maybe on the other side you have highly trained professionals. They use the full array of your operators, and they can create pretty complex queries, and then kind of folks in the middle. So again, what is the problem we're trying to address with query parsers? Well, maybe this is the first relevancy issue, which is how do I translate what the end user provided, whatever that expression is, into an executable representation of that most effectively approximate the intent. And this will always be an approximation, right? And so the question is, how closely are you approximating? So yeah, this is basically recall. And so if you don't get your queries right, then this is kind of a bad start. So what can we do out of the box? The topic is about custom query parsers, but let's make sure that before we engage into a long journey writing custom query parsers, let's kind of take a look at what we do out of the box. And you can do a lot, as you all know. Both Solr and Elasticsearch have a pretty long catalog of query parsers that we can use, and we all know and love the classic Lucene, of course. That's sort of the first thing we learn as a search engineer, right? And then you kind of get to the edismax. I like to call it the Swiss Army knife. It's got so many things on this thing that sometimes it's hard to know how to use it. And so the edismax query parser, oh, the colors are not very good here, I apologize. It says, I love search. So the edismax, we're going to get kind of techie here. The edismax is a good natural language query parser. And it takes a bunch of terms and turns it into this query here where it's a disjunction max, right? And which is in this case is term-centric, right? So that's kind of the contract offered by the edismax. And so that's what it does. And I guess the next question, as you contemplate how you user search, is how far can I go? And for example, let's say you want to, as kind of a wink to this Green New Deal legislation that Democrats have proposed in Congress about a couple months ago or so. What if you actually look for, sorry, wrong button. You look for the capitalized term green because you're looking for that green, new deal, but not the adjective green, right? Not the lowercase. That is 5 positions or less before the noun deal, right? Kind of an example query. Your product managers ask you to implement that. So, hey, no sweat. I can just, my first approximation is Lucene phrase. I put some slop. It's pretty good. It's not exactly what your product manager is asking for. Certainly, I'm not doing anything about the capitalized term, and I'm not doing anything about order, right? The slop doesn't enforce any order, right? But it might be that, as you run your judgment list and you look at your metrics, this might be a pretty good approximation. It may actually provide some good results. Now, the next sort of iteration of sophistication from that is to maybe use something that's not very well known, the surround query parser in Solr, which is essentially a conduit to the span queries in Lucene. And so what you can do is start specifying an order. So this is the infix notation of the surround query parser, where you said that green has to be 5 positions before a deal, which you couldn't do with the phrase query with Lucene, right? So right there, that's a pretty good capability at your disposal. The other thing that's cool about the surround query parser is that it's nestable, just like span queries in Lucene are nestable, which is an awesome capability. You can say span, and here I'm using actually the prefix notation. So span green deal within 2 positions of each other in order is 5 positions, 2 positions. So the span green deal is within 5 positions of Congress or legislation. So I've got a pretty good amount of complexity here. I've got a nested span, and I'm also using essentially a Boolean sort of and of the other span, right? So yeah, this is one of the query parsers in the catalog that's not very well known. It's got a lot of power. Now, what we really want to do is more something like this. Hopefully you can read at the bottom of the screen here. So I've got 2 hypothetical custom query parsers that don't exist. These are mine as a capitalized query parser because that's how I specify my green condition. And then I've got my own proximity, and I'll explain why I need to have my own proximity query parser. And then I use composition with this notation here. How many of you have seen this notation before, the underscore query underscore? Okay, just a few. That's not very well known either. But that's kind of the compact form of composition, right? And you can have nesting, grouping, and or not, et cetera, and basically mix and match. So that's kind of what I would like to produce that I'd like to send to Solr, right? So on the topic of composition, the blue doesn't come through again. I've counted 29 query parsers in Solr 7.7. The Solr 8 doc is not out yet, by the way. I don't know if you guys noticed. And yeah, so you can do something like this, which is fully composable. Same notation here, this compact notation, where I can mix and match different things, right? You can do the same thing with the XML query parser, if you haven't seen that. Same query, more verbose, of course. But this might be a better output if you are programmatically producing this, right? And you can also express the same query in the JSON query parser, right? Which is sort of the latest kid on the block in Solr, and this is where you see Solr trying to be like Elasticsearch. Same query as before. So, what if that's not enough? What if we need to go beyond? So, and why would you want to go beyond? Well, in this project I just mentioned in the beginning that I'm currently working on, we were really hoping to actually take full advantage of the existing query parsers and not get into the custom query parser. That was sort of the first tack we had. And well, we kind of ran into some limitations and quirks. For example, the surround query parser. So we had a lot of spanning, a lot of proximity type operators to implement. And we realized that the distance is only up to 99. It's like, why? I don't know. It's in a Java CC grammar. The designer decided to limit it to 99. It's very arbitrary. And I was not, we were not going to go in there and change that particular grammar. And then even more bizarre, the terms you feed to the surround query parser are not analyzed. The query parser doesn't analyze these terms. So So if you were here during Tom's presentation, he has a step where he says you have to analyze your terms. So that I don't know why the surround query parser author didn't do analysis. If you guys know this, I'd love to hear about it at the end of the talk. So, and then of course the other situation where you're going to have to start thinking what's beyond is if there are some operators that just don't exist. What if you need to do capitalization? Right? Something is capitalized first letter. Something is all capitalized. And this might be important for some applications. What if you need to express a frequency requirement? Like something has to match so many times or less that we're seeing in some applications. Or some kind of as-is operator to essentially defeat the stemmer. I don't know if you've ever had to put a keyword marker filter in your analysis to tell the porter stemmer, please don't stem this, or, that's kind of classic. And it's a pain because you have to produce a static list of terms. So, yeah, so they may be operators that just don't exist, right? So what do you do then? Well, then enter the world of custom query parser. All right, so what we're going to do now is going to be very ambitious for me as a presenter here. Is to actually build a custom query parser with you. So get your laptops out. No, just kidding. So we're going to go ahead and we're going to build a new proximity query parser because we want to remove the distance limitation and we want to analyze the terms, right? And so we're going to use the same notation as the existing surround parser with the W distance or N. So W is in order, N is unordered. And go play with the GitHub project here. It's got the proximity query parser as well as the capitalization query parser to play with. Okay, and so basically imagine that the Q string is Cville haystack within 5 positional rocks 2019. So what the query parser is going to try to do or is doing. It's going to pick up on the fact that there's a proximity clause here, which is going to take precedence over the other terms. And we're going to build a Lucene query to essentially execute this, or to approximate what we think the intent is. All right, so this is where it gets kind of ambitious here. Never done this before. All right. So, actually, no, too fast. Hang on. A little bit of preparation. All right, let's go over the basic anatomy of custom query parser in Solr. The touch points between the Solr and then your code are pretty minimal. You'll start with a factory class. So if you're a Java developer, that'll look familiar. This factory class, you give it whatever name you want. It has to extend this Q parser plugin. And all you have to do is implement this create parser, which creates another object of type Q parser. So we'll have another class here to talk about. Once you've got your factory class, then you declare it in your config this way with the query parser tag. And you give it a name, whatever you want. I call it proximity here, and you give it the Java class package. This will be loaded at startup time and put on the class path. Once you've got your query parser, then you use it with the good old def type to specify your query parser in a request handler. And so what's nice about the way Solr it kind of delineates responsibilities is that in my request handler, I specify my proximity def type, but then it doesn't limit me in any of the other things I do in the request handler, right? Because I can do, and I'm sorry, the colors are terrible. I can continue to do all the boosting and custom scoring that I, like and love to do. You can specify your highlighting, your faceting, so everything else you do in your request handler, stays valid. The other class, so let's back up here. So the factory class is essentially producing, that's why it's a factory, it's producing this, this Q parser object. So let's take a look at that. So that's the other touch point. Here's our QParser object. And the constructor is not doing a whole lot. It's basically passing on to its parent all the parameters. All you have to do is implement the parse method. And its sole purpose in life here is to produce the Lucene query and return it to Solr. So what's nice about this division of labor, so to speak, is that as a query parser plugin writer, I'm not responsible for executing the query. I'm just building the query, which means that I don't concern myself with pagination, filtering, highlighting, faceting, so on and so forth. I'm not even concerning myself with scoring, unless I have to get into custom scoring, which will probably be my talk in Haystack 2020. But that's a nice division of labor. I'm just going to concern myself with building a Lucene query. All right, before we actually dig into the code, this is actually be a slide, if you were here in the talk before, that's going to look very similar to what Tom presented. So I call it the parse flow. It's not as elaborate as Tom's slide. But since we want to do a simple demo of the code here, so again, let's see what happens, what you have to do as an implementer of this functionality is step one, you have to parse, of course, and producing the AST tree, which is a fancy name, abstract syntax tree. The tree is a representation of all your operators and their operands, and all the precedence rules have been figured out. So it's all laid out nicely, and it's a really nice structure to actually traverse in software. So that's step one. Step two is the analysis of the search terms, a search phrase at the leaves of the tree, right? So this is where you're going to find yourself, taking haystack, lowercase, taking rocks, lowercase, remove the exclamation mark. Whatever you have in your analysis is happening here, right? And curiously enough, again, the surround query parser out of the box apparently doesn't do this. And then finally, you walk the tree to produce a Lucene query to match. Maybe you walk this tree several times for different purposes. First, you generate a search query. Maybe you walk it again to generate a highlighting query. And there may be other usage. And that's a really nice pattern in this sort of parsing applications where you create this AST, this parse tree, which is then used for different purposes. So an example of why you would have different queries between searching and highlighting is when you highlight, maybe you prune all the not conditions, right? You don't need to highlight things that you're not matching. Okay, so this is where it gets ambitious. We're going to do a little bit of review of the Java code because what I'd like to show you is that this is a very approachable thing to do. There's not a whole lot of code. Now, I'm not going to show you an antler grammar, right? This is not the objective. I want to show you kind of the boilerplate code that's within a query parser, right? And probably will not have time to show you the unit test, but there's a ton of unit tests you can perform when you generate these plugins. And we'll run some queries and maybe examine scoring. All right. So this is where I go to IntelliJ, which is the best IDE in the world. Eric disagrees, but. All right, so that's our factory class, right? All I have to do is implement the create parser, and I instantiate my QParser class. So here it is. I'm just going to drill down. So what do I have to do in there? All I have to do is implement the parse method. And so this is where all the work happens. Check on time. Okay. So let me point out a couple of things. Typically in the query parser, you will have a bunch of parameters that you want to grab. And so for example, here we have a QF, query field. I kind of borrowed that name from EDSMAX. At the moment, this very simple code is single field, modo field. Also, I have an MM, minimum should match, because we're here for relevancy, so we want to play with that. And so these parameters are essentially kind of handed to you as in this class, and they're either coming from URL parameters or they're coming from your request handler, right? So you get all these parameters kind of delivered to you. Then the next thing we're going to do is grab the query time analyzer because part of our functional specifications in this query parser is we want to analyze the terms, right? We want to do better than the surround query parser. So very easy to do. We grab this REQ request, which is right here, handed to us. We get the core. We've been loaded for, the schema, the field type of QF, and then the query time analyzer. So now I've got this object here, analyzer, that represents what I configured in the schema.xml. Then, just to kind of make the code more modular, here I instantiate essentially an implementation class. So, I was experimenting with different implementations of this. So here I have a simple implementation of our proximity query parser. I turn the into a number, and then I delegate the parsing to that implementation class. So this is where basically the work is going to happen. In this project, actually, I have three implementations of different things. So when you look at that in the Git repo, if you're interested, you'll see the simple class, the simple implementation I'm going to show. There is a more elaborate implementation that supports phrases. And then there's this capitalization query parser I want to have time to cover now. All right, so let's take a look at the simple implementation. So hopefully that's not too much code. Again, I'm kind of trying to show you the touch points and the boilerplate, right? So to follow our flow, where we had step 1, parse, step 2, analyze, step 3, generation of the query, I put some comments in there to kind of help follow that. So the first step here is actually combining 1 and 2, where this helper method is gonna parse the string and is gonna produce the AST. And we also deliver an AST that's got all the terms analyzed. So because this is not production code, my parser is essentially a regular expression, just for demo purposes, right? So all I'm doing is breaking up my search string by looking at the operator in the middle, everything to the left, and everything to the right. Now, again, this is not production code. If we were developing an extensive grammar, I'd use probably Antler for that. Now, where it gets interesting, I think, maybe you haven't seen this before, is that, by contract, we're analyzing the terms. This is something we must do. So let me kind of show you the code for the analyzer, which is, kind of well put together in Lucene. All you have to do is, what you do is get a token stream class. You tell the token stream what you're interested in collecting. So here we want to collect the char term attribute, which is actually the text, the bytes out of the analysis. And then you essentially, in this while loop, you collect all the tokens at the bottom of your analysis chain, right? Essentially, this code here is what you see on the Solr UI when you go through the analysis UI, right? It's the text is traversing the entire pipeline, and then you collect the terms at the bottom. Now, one thing I'll point out, if you look at this code later on in the repo, is that it is completely ignoring issues of token graphs. So if you're familiar with this problem, filters like synonyms graph filter, word delimiter graph filter, maybe others, filters, token filters that can produce actually graphs, arcs of actually valid sequences of terms. My collector here is completely ignoring that. So I'm getting all the tokens in one flat list. Now, in production code, you can't do that. The reason these filters produce graphs is for the query parser to be aware that they are valid sequences of terms in the token stream that you have to adhere to or respect. We're doing on time here. 26, okay. All right, so let's go back where we were. So far we've broken the string into 3 parts. We got the left side, the operator, the right side. We've analyzed our left sides. Now we have left terms and then right terms. And at that point, one more thing before I generate a Lucene. Right, so then I have to extract the distance in the operator out of that block in the middle, right? So I get my in order and I get my distance. again, this is all demo code to kind of give you the boilerplate. And then in a sort of very simplistic fashion, I return my AST tree. That's my AST tree, right? Very simplistic. It's composed of a root node, and then which is the operator with the distance and ordering attributes, and then there's a left side and then a right side, right? So there's a super simple AST tree. Operator, distance, in order, left terms, right terms. That's just an object to kind of contain all this and send it back to the prior method. So we're done with the parse tree. Now we're back here, almost done with the code review, by the way. So hang with me. So we've got our parse tree here. It's got the tree, and all the search terms have been analyzed, right? So we're in a good shape now. We can walk this tree and do what we need to do. And so that's the next step, which is a step 3 in the flow, right? Where we're going to walk this tree and we're going to produce the Lucene query we're looking for. Now, this is where query parsers are really awesome, because what you do with the tree is completely up to your requirements, right? You have a really nice data structure here, theoretically. I mean, this is a silly one here. To generate search queries, highlight queries, maybe you can extract filters. I think Tom mentioned that in the previous talk, where you can do like auto detection of filters, I think, something like that. And maybe you can also do synonyms expansion at that point. So all kinds of things in the query cooking that has been referred to in the previous talk. So here our cooking is going to be to produce essentially this, where we're going to definitely kind of isolate the proximity clause, and everything that's to the left, we'll just basically OR them together as single terms, and everything that's left over on the right, also ORing together as single terms. Right? So that's my cooking right here. That's the cake I'm trying to bake here, to use that analogy. All right, so after that, it's kind of your mundane code of looping around and creating the proper classes. So here I'm grabbing all the terms to the left and generating the most basic primitive in Lucene, which is a single term query, right? So this is the Java class to say I want to match on this field on this term, right? And so at that point, the loop is basically just kind of stacking up all these individual term queries. Then I'll produce the proximity clause. And here, it's very satisfying to take advantage of the rich set of span queries that Lucene offers. So here I'm using a span near query, which is exactly the contract I'm looking for. Right? I specify to it an array of span queries. Span queries are nestable, so you give it additional spans, and you can go sort of ad infinitum. Then you get into garbage collector if you go ad infinitum. And then over here, we're doing the same thing that we did above. We kind of collecting all the leftover terms to the right, and putting them in the list. So now we have all our clauses built, and then we're going to use this really handy Boolean builder pattern to construct the final OR query. And so first, I'm actually taking advantage of the fact that the builder has a notion of minimum should match. So I'm basically just going to invoke that method out of the builder with my main match. So that's very cool. I don't have to actually implement that, which would be kind of tricky, but possible. Then I loop over my terms on the left and add them up using the builder as a should clause. Then I add my proximity clause. Everything, all of these are should, and same thing for the right side terms. And I call .build, and I am done. I have built the query. I have cooked the query I wanted to cook. So what does it look like? We'll do kind of a simple proximity here. So I'm using Postman here because it's kind of easier to see things. So here's an example of how you would use this. So here's an example. So curly brace, bang, proximity, right? That's the notation to specify a query parsers. I specify my QF equal title T, and then green all uppercase within 100 positions of deal. Now the reason, this looks absolutely silly, right? But I just wanted to demonstrate that I do analyze the terms, and I can do above 99, just as a kind of a silly test. So let's run that. And so we do get my test corpus has a grand total of 1 document. So I don't have any data ingestion challenges. So that's the text here. And so cool, rematching. And then we actually, what's very satisfying to see is the query that we generated. That's exactly what we would expect. Here's our span near, title T green, title T deal. Here's our positioning and our in order set to true. And then this little guy over here, tilde1 is your symbol. And there's only 1 clause, so that's going to be a tilde1. So you can see that we analyze the terms because it's green lowercase, deal well, I guess there was nothing to do for deal, but we can see that green has been analyzed. The scoring is going to work as expected. The scoring is something that's provided by the Lucene queries you are using, and the scoring is composed per your composition of the Lucene queries. So if you're doing a bunch of OR, you're going to basically add up all the scores where you match, right? So it kind of works as expected. So unless you have to do custom scoring in your query parser, then you really don't have to worry about that. And again, custom scoring is yet another talk for another time. All right, and then I'm going to show you basically something else with the cap. So here, it's sort of answering the final question that was on the slide, where, so I want to look for green capitalized first cap. So that, everything is my invention, right? The first cap operator, I came up with this, right? That's part of my grammar, right? So I want to match green only first cap, and then I've got my proximity between green and deal, right? So we'll go ahead and run that. And we match our single document, and then let's take a look at the query, right? We see at the end here the span near query, right? That you would expect, green deal, and then the capitalization is implemented with this span payload check query. So again, I don't have a whole lot of time to talk about the capitalization, but the span payload check query is a primitive in Lucene, which allows you to say, I want to match on green, but also on payload letter F. Now, letter F was just my convention to denote a term which was capitalized. Now, this relies on a, if I can find it here, this relies on a index time filter. So we have here a custom filter that's part of the solution here. It's called capitalization payload token filter. And so what I'm doing here is in that filter that's like half a page long of code, I just look at whether there's a capital letter in there. And then if there is, then I put in a payload, an attribute that tells me whether it's first letter capital or it's all caps or whatever, right? So that's something I can then take advantage of. If I go back to Postman, take a look at query. Yeah, so here's my F letter, so it will match on the first case green, first letter capitalized. Okay, so I think we're getting close here. How much time do I have? About 10 minutes. Okay, so yeah, so maybe I have time to show you this unit test stuff, which is pretty cool. One of the great things we can do as plugin writers is the amount of unit tests we can perform. So, and this is just kind of one possibility. There are others, but this class here is fantastic. This is a RAM-based Lucene index you can spin up in RAM in your unit test, in your JUnit test, right? And then once you spin that up, then you can go ahead and add documents to that index. And again, the index is spun up every time you run the test, right? Completely from scratch, completely repeatable. So you add some docs, you know, the quick brown fox jumps over the lazy dog. And then once you have that index in place, then you can start doing a test as shown here. So I'll kind of walk you through this unit test where I mean, we won't do this one. Let's see, simpler one. Yeah. So we're going to verify that we are producing the proper query for fox W4 dog, right? So first thing is we're going to actually invoke our implementation to get the actual query that our code produces. And then we're going to build the query we think we should be getting, right? So we're going to basically manually generate the span query by hand using the primitives and finish with an expected query over here, right? So here's my span near query. I'm doing the builder pattern in order to set my MM. I only have one clause here, but I'm still kind of wrapping this on the Boolean query. Once I've got the expected query, then I can do my assert. Is the expected the same as actual? And if so, if not, I'm going to bomb here. But if so, then I can also actually do searching on that RAM-based leucine index. So I'll basically do an assert on the number of hits. And I could go as deep as I wanted, you know, document by document, verifying that I got the docs in the order I'm expecting, and actually even get to the point where, you know, I could you know, get title and do an assert on the actual title also. So a tremendous amount of capabilities here, and really exhaustively test all kinds of use cases with the unit test. The deploy, I guess I'll say something quick about that because it's always tricky. If I have my, so plugins can be deployed different ways. The super simple way, which is still very possible even in a production environment, is you actually tell in a Solr config where your jars reside. You know, I don't know if you've seen this before, right? So even in a Solr cloud environment with many nodes, you can essentially have you know, a Jenkins script or some other sort of orchestration that will push your jars, you know, one or several, to a location that is known by the node. Another maybe sort of tighter way to deploy jars is through the blob. The blob API of Solr, orchestrated by Zookeeper. But if you're interested in that, come talk to me at the end because it's kind of tricky. Okay, I think we're almost done. A few minutes left, right? 5 minutes or so. All right, we talked about scoring, working as expected, so I can skip that. All right, so let's spend 1 minute on this because this is kind of important. It kind of wraps up the design options that we've seen. So I've seen sort of three approaches here for query parsers in general. The first one is basically, you know, out of the box, your users are using natural language, right? So the edismax will work perfectly well, right? Notwithstanding all the tuning effort you have to spend on that, right? The second approach is actually something that I think Tom showed us in the previous talk, where you rely on the ability of your solution to generate something that can be executed by Solr out of the box, right? You use the query composition. You can still have within the application layer a parser, a query generator to implement your custom query language, but you're not asking Solr to parse. You're using the out-of-the-box query parsers in some kind of composition, right? And a note to my client in the room, this is what we initially try to accomplish in the fall. And then lastly was the second part of my talk here, where we actually implemented inside Solr a custom query parser that is taking whatever the end user type, or something like this, by the way, right? This is where it gets interesting, because once I have custom query parsers inside Solr, then I can compose them in the same manner that I can compose, you know, any other query parsers. So quickly, pros and cons of these three approaches. I'm probably running out of time. So in terms of the amount of software R&D, as expected, whoa, too fast. So there's nothing to do for eDismax. And I'm talking about software development here, right? I would say between the second and then the third options, which I call composition versus custom, it's probably moderate versus high. I mean, I think here is a custom query parser is sort of the most intense software development effort. Ease of Solr upgrade, that's kind of important. What happens when you upgrade Solr? Is it going to break everything? Of course, you don't have any issue when you're using out of the box, but here it's going to have to be managed, right? You're going to have to make sure you test, make sure everything is working. And apparently, this exercise here is much easier in Solr than in Elasticsearch. I was talking to Jetro is not in the room, I don't think. I was talking to Jetro, one of the Elasticsearch LTR plugin. He was telling me that from version to version, there's all kinds of stuff that breaks. I don't think I've seen this with Solr, which means that maybe Solr is like open for business for plugins, not as much for Elasticsearch. In terms of performance, of course, that there are two things that can kill a search application. One is bad relevancy. The other is bad performance. Keep your finger on the pulse performance-wise. You're going to be good if you use out of the box. In the custom query parser, I would say if you parse once as opposed to many times here, then intuitively you'll have better performance. But of course, be careful what you write, right? I mean, with great power comes great responsibility. Deployment, we talked briefly about how to deploy in jar. Not a huge deal here. This is not a red flag. I think it's well understood how that's done. And now finally, ease of relevancy tuning. So that gets interesting, right? So eDismax, we know what to do here. That's painful. Probably even more painful when you start composing different query parsers. And then over here, it gets interesting because you're like, oh, wait a minute. I actually need to implement term-centric versus field-centric. Oh, gee, I have to implement MM. All these things you have in the eDismax that you kind of took for granted, you may find yourself having to re-implement some of that behavior over here. So that's a little bit of a red flag. Last consideration, if there is time, maybe 1 minute. So when you think about your query parsers and your query parsing pipeline in general, and again, Tom had a nice slide on this, is that you may want to think about where things fit the best. So for example, if you do complex entities recognition and you have a service out there doing that, maybe this is something that your search service layer is handling before you give the queue string, so to speak, to Solr Cloud or Solr. So think about how best to divide responsibilities. So in this architecture here, hypothetical, the architect decided to do entities recognition first and then pass on to Solr a search string that has the recognized entities kind of figure it out already. Now, of course, in this case, we still have to go through the parsing to create the AST. But it's not always obvious that everything has to be in Solr or everything has to be outside of Solr, right? So it's like, where do you draw the boundary between the different functions? All right, closing remarks. I'll say that query parsers are a lot of fun, and that they have a lot of power. But do make sure that you fully analyze your requirements and you fully analyze the capabilities of Solr before you get into that, right? You may be able to do just fine with the out-of-the-box. With great power comes great responsibility, particularly in terms of performance. So be careful about that and test performance as early as possible. The relevancy knobs and dials can be tricky to re-implement. Just touched upon that a minute ago, right? Doug has written 3 chapters about this, right? You all read these 3 chapters, I imagine. By the way, boosting can be done either inside the plugin or outside. There are options there as well. And kind of a final statement, because I'm interested in the nuts and bolts of things. You're right, Eric, I am an engineer. I love the kind of lifting the hood and seeing what's happening underneath it. So my next frontier, personally, is to kind of get into custom queries, like what if I don't have a primitive Lucene query? So for example, something that has been frustrating me a great deal, my talk last year at a Haystack was about multi-term synonyms. Who attended that talk, just out of curiosity? 1, 2, oh, okay, great. So this has been like an ongoing pain in the neck. And there is actually a synonym Lucene primitive, but it only works with single terms. So I'd be interested in seeing how we can create our custom Lucene query specifically about multi-term synonyms and to kind of equalize scoring as well. And maybe some kind of frequency operators. And that concludes my talk. Thank you very much.